and think about what we're going to do overall. And as I mentioned at the very beginning, it just seems like a lot of information. It's because it is. If it seems like we're going through it relatively rapidly, it's probably because we are. Not sure of a better or a different way to do that in our limited time. But the key thing is to note all of the similarities here. So as I mentioned in that thrilling video, there's 5 reactions that we're going to cover. Then what we want to think about are the effects of substituents. Groups on the benzene ring. So we'll have an effect known as activating or deactivating, which basically means it reacts faster or slower than benzene. And then we want to consider what are known as directing effects. This is probably the most complicated part of this, but we'll see it's very systematic. And we have orthoparadirectors and we have metadirectors. So we get back into that language. Then we have a few other reactions. I'm not sure if we'll get to this today, we'll see. And then finally, very briefly, rather than electrophilic aromatic substitution, we have nucleophilic aromatic substitution. That's a substitution, I think, and that's 2 reactions. Either we add and then we eliminate, or we eliminate and then we add. So that's the outline. I put it on the right, but I probably didn't leave enough space on the left to direct reaction, so I guess we'll just leave it as it is, like that, and we'll write down below here. So we saw last time, so we'll fill it in with this. Okay, so we have this reaction where we can take our benzene ring, and we'll use benzene over and over for this. We have our strong electrophile of E+, just like in that generic reaction, we used benzene last time, right? Remember, so in the same reaction, we pay this large energetic cost to form the bond with the electrophile. I'm rewriting essentially the same thing. We have a carbocation intermediate that's resonance stabilized, and then we're going to have something, space, pull this proton off to reform our benzene ring, substitute it with the electrophile. So we first use bromine plus a Lewis acid, FeBr3. So that was 1A, and that was the reaction we covered on Thursday, and we used this to brominate the benzene ring. You can also use chlorine. You can chlorinate the benzene ring. This is normally done rather than with FeBr3, is with AlCl3, aluminum trichloride, and that's more for a practical reason. So on paper, you could use FeAl3 if you wanted to, or something like that, but it doesn't really matter so much. Usually, fluorine it reacts too fast, and iodine reacts too slow. So these reactions, if you see them a lot for just bromine and chlorine, and asking yourself, well, what about fluorine and iodine? It's because these two, bromine and chlorine, are kind of more in the sweet spot for reactivity. There are ways to carry out these reactions, in particular with iodination, to add an iodine or iodide to the ring, but we'll stick primarily with bromine and chlorine. So that was actually one of our 5 reactions. Let's look at the next one here. And I did put this one on the video because I wanted to use it for those directing effects, but let's just go through it very quickly here. So this is nitration here. And the observation is we can take benzene and react this with nitric acid, HNO3, and sulfuric acid, 2 strong acids, and we end up substituting a hydrogen on the ring, a proton, with the nitro group. So we've nitrated the ring. So let's use this to evaluate those 3 steps of the mechanism. So the first one we're going to do is we're going to generate the strong electrophile. And this is really the only step that is different. And this seems a little odd in a way. Let's put the nitrogen here. So let's write out nitric acid with its formal charges. And let's have this now in the presence of sulfuric acid. So even though these are both acidic compounds, sulfuric acid is a stronger acid than nitric acid. So sulfuric acid actually protonates nitric acid, and that's what was described in the video. All of this is the same. So now what we've done is we've introduced a good leaving group. We have water as a leaving group. So now we can kick this out. And we formed this species here, which is known as the nitronium ion. And so we have that nitrogen now with the positive charge. And so this is going to be our strong electrophile. And I'm going through this fast because hopefully it's on the video for a reference so that we can spend more time on the newer stuff. So the idea here is there's our strong electrophile. Rather than Br plus equivalent, it's now this nitronium ion. But the same idea, the benzene ring is going to act as a nucleophile. We'll just put the nitro in the same spot as with the bromine. So now we have N, looks like this, for the nitro group. Sorry, can't really see that positive formal charge. And now we have a formal charge on this particular carbon. So we can regenerate our aromatic system by having, let's just have water that was lost from the nitric acid. This is our weak base. Pull the proton off. And this generates NO2. Overall neutral, and we've reformed our aromatic system. So this is really step 1B. This is step, I don't know what the 1 is doing here. Sorry, let's A is to generate the strong electrophile. B was to generate the rhenium ion. And then C, here was our step to deprotonate, about regenerate aromatic system. Okay, so same idea as before, but the thing is that we have a different first step to generate our strong electrophile here on the top. It happens to be this nitronium ion. This is actually quite useful here to generate this nitro group because we could actually turn this into an amine. So I'll just draw it here as a reference. We can convert the nitro group to an amine. We're not going to go through any sort of a mechanism for this reaction. It's a mystery, but this is a useful synthetic tool. And really could use our classic hydrogen with platinum or palladium. Is typically on carbon. And this will turn that NO2 group, so it's a reduction reaction, to an amine, to NH2. Or if you're reading about it and you see this tin chloride, is another set of reagents. I don't expect us to memorize these. Or if that's not enough, how about zinc with acetic acid? But the key thing is, for those interested in this in terms of the synthesis, the nitro group is useful because you can also turn it into this amine. This is aniline for our common names. And then this nitrogen can be used in a lot of other chemistry. So that's where the nitration actually has a lot of other applications. Okay, so now we have two reactions. So, sorry, Kyle, this is supposed to say C. And what this is representing is the palladium metal is actually deposited on carbon. So this is a bit of a jargon here, how this reagent occurs. It's known as palladium on carbon. And it's a way of delivering the palladium. So there C stands for carbon.